Now we'll design a mod 5 up counter. A mod 5 up counter means a counter which will have only 5 counting sequence. Only 5 counting sequence means it should be resetted when 6th count comes. With 3 flip-flop we can have 2 raised to power 3 means total 8 counts. With the 2 flip-flops 2 raised to power 2 equal to 4 counts. 4 counts are possible only with 2 flip-flop. So we will have to use 3 flip-flops so that 5 counts can be possible. For up counter we will have negative edge triggering, Q as a clock, this will be Q2, Q1, Q0. Initially all the output will be resetted 0 0 0. After applying first clock pulse it will start counting the clock pulses. Now we have this as first count 0 0 0, this as second count, this as third count, this as fourth count, this as fifth count. Total 5 counts are completed. For mod 5 counter this is not a valid count. If this count comes it must be resetted. So to reset the flip-flops we will have to design or employ one more signal which will be called reset signal. If we have logic 1 at this reset signal, all the flip-flops will be resetted again to 0 0. To have logic 1 at this reset signal, we will have to derive this signal from the flip-flop output itself. At this count Q2 is 1, so we will take this output. Q1 is 0, so we will take Q0, Q1 bar, not Q1. Q1 is 0, Q1 bar will be taken. And Q0 is 1, so this Q0 will be taken and all the 3 will be passed through an AND gate, and this AND gate output will be the reset signal for these flip-flops. And we know that at this AND gate all the inputs will become logic 1 only for this count. For any other count there is no possibility of coming all the output logic 1. If all the output logic 1, then only the output will be logic 1, otherwise the output will be logic 0. So when 101 comes, this AND gate will give input logic 1 to all the reset inputs, and after the fifth clock pulses, data of the flip-flop will again become 0 0 0. So this counter will be resetted. So in this way we can design a mod 5 counter. Same is the process for down counter also. Now we'll see BCD counter or mod 10 counter. There will be total 10 counts. We know that with 3 flip-flops, 2 raised to power 3 total 8 counts are possible. So 3 flip-flop are not sufficient. We will have to use 4 flip-flops at least. With 4 flip-flop, maximum count is 16. So 10 counts can be obtained. All the flip-flop will have their input logic 1. At this time we will take T flip-flop. A toggle flip-flop can also be used, but it should have its input T equal to 1. All the flip-flop will be negative edge triggered flip-flops. Now in BCD counter, from 0 to 9 it will count. The ninth count will be 1001 and the 10th count will be 1010. But the 10th count will be its 11th count, because 0 to 9 it will have 10 counts. After 10th clock pulse it will have 11th count. So for this 11th count it should be resetted 0000. For this we have Q3, Q2, Q1, Q0 as 1010. So we will take this Q3 because it is 1, Q2 bar because it is 0, Q1 because it is 1, and Q0 bar because it is logic 0. And all these will be passed through an AND gate, will be applied to the reset input of the flip-flops, and the design will be similar. In this way, this flip-flop, this counter will be resetted whenever the count is 1010. So this is a mod 10 or BCD counter. Remember one thing, that the output at this Q3 will have frequency f by 10. If frequency of input clock is f, this output will have a frequency f by 10. Synchronous counters. As already discussed, a synchronous counter will have all the flip-flops applied with the same clock. In synchronous counter, the first type will be, simplest one will be ring counter. Ring counter is a special purpose counter which has some definite counts. It is similar to that of shift register. Now in this counter, all the flip-flops will be applied with same clock. Remember that positive edge triggering or negative edge triggering both will have same operation in these types of flip-flops. Now in the ring counter, the last flip-flop output will be given in the feedback to the first flip-flop input. D flip-flops are used means bits will be shifted, just shifted, and uh, if the first count, initial count is suppose 1000, then the count will be changed at each clock pulse, and this change will be noted. We'll start the operation. We'll write its truth table. Q3, Q2, Q1, Q0, and this is clock. Suppose initially we have zeroth clock and all the flip-flops are in their initial state. Initial state will be 1000. First flip-flop will contain 1. Second flip-flop 0. Now this 1 will be available output here. This 0 will be available at the output here. This 0 will be available at the output here. And this 0 will be available at the input here. Note one thing. Before this, we studied asynchronous counter in which first flip-flop operated, then next flip-flop will operate, then the next to that will be operated. But in these synchronous counters, same clock pulse is applied, all the flip-flops will be triggered at the same time. So inputs should be arranged prior to the applying clock pulse. Now, when first clock pulse is applied, this one will be stored in this flip-flop, this 0 will be stored in this flip-flop, this 0 will be stored in this flip-flop, and this 0 will be stored in this flip-flop. Means this 0 bit will come here and all the bits will be shifted. Again, the same operation, this 0 will be here, all the bits will be shifted. Sorry, this will be logic 1. All the bits will be shifted, this 0 will come here, all the bits will be shifted, and this one come here, all the bits will be shifted. So in this way we get different counts. If we see that these four counts are different from each other, this fifth count is similar to this one, this count is similar to this one, so we have only four states which can be used while other states are repeated. So these 8 states will be unused. 8 states or sorry, 12 states will be unused because 4 flip-flops total 16 states are possible. So in a ring counter, number of used states equal to n, where n is number of flip-flop, number of unused states is equal to 2 raised to power n, total number of states possible, minus used states n. Means these many numbers of unused states are there in a ring counter.
Now the next type of synchronous counter is Johnson's counter. It is also called as twisted ring counter. The twisted ring counter has a circuit similar to a simple ring counter with little difference. Both the ring counter and twisted ring counter are designed by making some modification to shift register. These are 4 D flip-flops. Like shift register, each flip-flop's output will be given as an input to the next flip-flop, and all the flip-flops will be applied with same clock. Now in ring counter, we have seen that Q0 was given as in feedback to D3, but in twisted ring counter, the output Q0 bar will be given as an input to the first flip-flop. Now we'll start the operation. Suppose in twisted ring counter we have initial count Q3, Q2, Q1, Q0 as 0, 0, 0, 0, and I will count the clock pulses which are applied to the flip-flops. Initially the count is 0, 0, 0, 0, so I will arrange all the input before applying the next clock pulse. All the flip-flop have logic 0 stored in them. This logic 0 will be available at the output of this flip-flop, means at the input of this flip-flop. This 0 will be available at the output of this flip-flop, means at the input of this flip-flop. Similarly, this 0 will be available at the input of this flip-flop, and as this flip-flop stores logic 0, output Q0 bar is logic 1, and this logic 1 will be input to D3. Now we'll apply the first clock pulse, first positive edge or first negative edge, depending on the flip-flop which are used, depending on the type of triggering of the flip-flops. It may be positive edge triggering or negative edge triggering. Now when the first clock pulse will be applied, this logic 1 will be stored in this flip-flop. This logic 0 will be stored in this flip-flop. This logic 0 will be stored in this flip-flop. This logic 0 will be stored in this flip-flop. Now at the end, when we applied the first clock pulse, now we can see that the flip-flop have data 1 0 0 0. So after first clock pulse, the data in the flip-flop is 1 0 0 0. Now before applying the second clock pulse, I will arrange all the inputs. Now the first flip-flop have logic 1 stored in it. This logic 1 will be input to the next flip-flop. This logic 0 will be input to the next flip-flop. This logic 0 will be input to the next flip-flop, and as this flip-flop stores logic 0, Q0 bar is logic 1, and this logic 1 will be available at the input to D3. Now when second clock pulse is applied, all the inputs will be stored in the D flip-flops. This flip-flop, this logic 1 will be stored in this flip-flop, and this logic 1 will be stored in this flip-flop, and rest of the two D flip-flops will be storing logic 0. So after second clock pulse, the data will be 1 1 0 0. Similarly, when third clock pulse will be applied, this logic 0 which is stored in D0, this logic 0 is available at Q0, so logic 1 will be available at Q0 bar. This one will be stored again in D3, and rest of the bits will be shifted on the right hand side, as we have seen earlier also. So this logic 0 will be complemented and will be stored in D3. and rest of the bits will be shifted. Again, after applying fourth clock pulse, this logic 0 will be complemented and will be stored in D3, and rest of the bits will be shifted to the right. Now when fifth clock pulse is applied, we'll see what happens. Before fifth clock pulse, all the flip-flop have logic 0 stored in them, logic 1 stored in them. Now this logic 1 will be available at the input to this flip-flop. This logic 1 will be input to this flip-flop. This logic 1 will be input to this flip-flop, and at the output Q0 there will be logic 1, and Q0 bar there will be logic 0. This 0 will be available as an input to D3. Now when fifth clock pulse will be applied, this logic 0 will store in this flip-flop, this 1 in this flip-flop, this logic 1 will be stored in D1, and this logic 1 will be stored in D0. So after fifth clock pulse, the data in the flip-flops will be 0 1 1 1. This 1 was complemented and will be stored in D3, so it will be available at the output Q3, and rest of the bits are just shifted to the right. Now when sixth clock pulse is applied, this logic 1 will be complemented and will be stored in Q3, so this bit will be 0 and rest of the bits will be shifted to the right. After applying seventh clock pulse, this logic 1 will be complemented and will be stored in D3. Rest of the bits will be shifted. After applying 8th clock pulse, this logic 1 will be complemented and will be stored in D3. Rest of the bits will be shifted to the right. Now we can see that this initial count and this count after 8 clock pulse are same, means repetition have started. So we can say that with 4 flip-flops from 0 to 7 we have total 8 used states. After 8 repetition has started, so with 4 flip-flops we know that 2 raised to power 4 equal to 16 states possible. We have already seen in ripple counters. In a counter with 4 flip-flop there are 16 states possible, but in a ring counter, twisted ring counter, we have only 8 used states. So we will not now conclude that in Johnson's counter used states are, here we have 4 flip-flops and we have used states equal to 8, means 4 flip-flop used states are 8. If there are n flip-flop, used states will be 2n, and number of unused states are 2 raised to power n minus 2n. So this was all about the twisted ring counter, Johnson's counter. Now, like asynchronous counters that we have seen ripple counter, in ripple counter we have the counts from 0000 to 1111, means we designed the counter to count up sequence, and also we designed the counters to count in the down sequence, that is from 1111 to 0000. So this up and down sequence is also possible in case of synchronous counter, but the design is a bit complicated.